Hi, Sec 3 chemistry students at Making Sense. My name is Mr. Lyman. We understand that some of you, your schools have started to teach acid bases and maybe even salt prep for WA2 or MYE. So we thought it'd be good to at least give you a free extra lesson, like a video recorded lesson. Not so much to go through intensively what the topic is about, but rather to cover the basic points of the chapter, what are some key things to take note of, and expose you to some of the questions that you will see. And most likely, maybe you will get careless mistakes, that kind of thing. Hopefully that sort of plugs some gaps and help you to revise for your exams or your tests, right? So this is a recorded lesson, which means that feel free to pause anytime you want. So as I'll keep going through the questions as we see them. So feel free to pause the video to attempt the questions first before I go through. Yep. So yeah, without further ado, let's dive right in. So for acids and bases, right, the first thing you guys learned is that an acid is a substance that dissolves in water to give H plus ions, hydrogen ions. Yes. So not that many things can do this, perform this. So in this case, let's say HCl. By itself, it is a simple covalent. You guys learned chem bonding already, so you can appreciate that this is a simple covalent molecule. When I put it in water, however, it's supposed to dissociate. So the word here is dissociate, to give H plus and Cl minus ions only in water, right? So right here, only in water, which means if there is no water, all right here, if no water, the HCl simply remains as a simple covalent HCl with no acidic properties. Okay, we'll talk about the acidic properties in a while, right? So the hallmark of acids is that they must dissolve in water to give H plus. Okay, this also means that not all substances that have H in them must be acidic, right? Only a few are like that. You learn only a few, right? So there's so many. Like for example, if I ask you for methane, CH4, sure it has 4H plus, but does it mean that if I put it in water, all 4H will come out as H plus? Not even, right? You recognize that your methane, if you remember the dot and cross for methane, it looks a bit like this. All of the H is covalently bonded. There's no way for the H to come out as H plus in water. And FYI, methane isn't even soluble in water, right? So the few that you learn, okay, at least the first three that you learn, right? These are your inorganic acids, in a sense that they don't contain organic compounds, inorganic acids, and these three coincidentally happen to be your strong acids. We'll talk about acid strength in just a moment, but what you do realize is that they have H in them, and you expect that since they're acidic, right, you put them in water, they will dissociate to give H plus ions. The other two are not so common. These are actually slightly weaker acids. In particular, this fellow here is an organic acid. You will see this a lot in Sec 4, but it's just good to introduce to your some examples of strong versus weak acids, so you won't get caught off guard when exams come, right? Okay, moving on. Some properties of acids. In Sec 1, Sec 2, you learn that acids pH are less than 7, right? There's a section on pH scale which we'll discuss later. Okay, I won't go through too much about all these basic properties because you sort of already know that it has sour taste, it turns damp blue, litmus paper red. It's able to conduct electricity due to the presence of mobile ions. Okay, this is pretty important, right? For those who sit in my classes, you know that I always say this. I'll say that in order for anything, what are the conditions for electrical conductivity? What are the things that any substance must have in order for it to conduct electricity? Number one, it must have charged particles. So when I say charged particles, I could mean a lot of things, anything that's charged. So H plus, electrons, ions, whatever. Number one, it must be charged. Number two, the charged particles must be mobile. If either of the criteria is missing, then it doesn't work. For example, solid NaCl. Sure, it does have ions, right? It's made of Na plus and Cl minus. But if these ions are stuck in fixed positions in a solid state, they are not mobile, right? If they're not mobile, obviously this fella cannot conduct electricity. You reverse the situation and you ask yourself, okay, methane is a gas at room temperature, so it's got a lot of mobile particles. They can move very freely, in fact, but are they charged? No, they're not. So they also cannot conduct electricity. So very specific conditions for electrical conductivity, which I need y'all to remember, like really remember it. Yep. Okay, one small thing, right? This portion here, Amine acids, you guys know that acids are pretty corrosive. Generally speaking, they are quite irritating, even at small concentration. Let's say you spill some acid on your hand during lab work, it gets itchy a bit. But I don't want you all to go away from this lesson thinking that as strong as an acid strength and its corrosiveness are related. They are not related to each other. Just because an acid is strong doesn't mean acid is corrosive. Okay, corrosion has a lot of other chemical reactions involved, most likely redox oxidation, which is something you'll cover later. Okay, so just bear that in mind, just a small thing. Okay, moving on. Let's talk about a bit of terminology. So basicity. Basicity in very layman terms, right? It's about how many bases can the acid react with. So you will see these words come out very commonly. If I say monobasic, the word mono here means one, right? Monobasic. Okay. Monobasic refers to the fact that it can react with 1 mole of base, right? If for those who haven't done mole concept on stoichiometry, okay, that's fine because it's not that tough to understand. It's like saying that if I have one of this, it should be able to react with one of this. No negative charge. Okay. If I put it even more simply, 1H plus is able to neutralize 1 OH in a neutralization reaction. That's actually what monobasic means. Mono base, one base. But unfortunately, as the days go by, right, people seem to correlate, can use it more loosely. So they seem to think that monobasic means, oh, it can dissociate to give 1H plus. Okay, I mean it's fine. It's not a terrible thing to do, but to be very technical about it, monobasic means can react with 1 mole of base, right? Therefore, it means that dibasic means that that particular molecule of acid can react with 2 bases. So for example, a dibasic acid would be something like H2SO4. Hey, you guys might learn in school that, oh, it's dibasic, right? H2, right? Maybe when you dissociate, it gives 2H plus. That's what the local, very informal definition of dibasic monobasic is. But in fact, what it means is that this acid later it can react with 2 of this. That is actually what it means. That's a very technical term. Okay, but as long as you understand what mono and di mean, that's good enough, right? You can ignore the monoproctic diproctic thing for now, unless you're IP or your H2, because the proctic here refers to a proton, which is something we will not talk about yet. Okay? Now let's talk about acid strength. For acid strength, we are very concerned with the extent of dissociation. So looking at this, a strong acid dissociates. Sometimes you see the word ionize. For the acid, it almost means the same thing. Because it becomes ions, ionized, right? Fully to produce H plus ions. Fully, 100%. Okay, 99 to 100%. Okay. So what it means is that if I am able to tell you, hey, I have 1,000 molecules of HCl. Okay, I put it in water. I can definitely predict and expect it to completely break up, totally, 100% break up, to give you 1,000 of this and 1,000 of that, with no HCl remaining. So you look at this diagram, right? At the start, I have 3 of this. Let me highlight this. I have 3 of this. It fully ionizes, fully dissociates to give you 1, 2, 3, and 1, 2, 3. None of the original HCl that was there, right, is not present anymore. All the HCl has broken up. So this is strong acid, 100% dissociation. A weak acid, on the other hand, is weak because the dissociation is partial, incomplete. So let me use the word incomplete. Which means to say, if I give you the same 3 particles of HX, where HX is a weak acid, I will most certainly not expect it to ionize, to dissociate 100%. In fact, as you go on a little bit more in chemistry and you learn about acids and bases and how they dissociate, you will find that a lot of weak acids dissociation is less than 1%, actually. It means I'll be very happy if I'm able to get 1% dissociation out of ethanoic acid. It's actually not possible. So look at this diagram, right? It's showing you that out of every 3 HX that exists, only 1 splits up. The rest remain largely undissociated. So this is something important that we must know. So that is strong versus weak. Okay, notice that this entire thing is just only about how well the acid breaks up. It has nothing to do with how well the acid corrodes your skin when we touch it. So I want you to remember that corrosiveness and strength are actually not related to each other. Okay, so that's that. Okay, so now let's talk about the dissociation equation. So you guys learned balancing equations before, and during the classes, your teachers will have taught you a little bit about how certain things react with certain things, what is the ratio in which the molecules will react, and that's what we're having here. Well, that's what we're going to do here. Of course, if you did more concept already, right, this would be even more relevant, right? Okay, so strong acid, dibasic sulfuric acid. Yes. So H2 sulfuric acid exists as H2SO4. Okay, you should know this by now. And because it's a complete dissociation, the arrow that I use is like that. One direction. Ooh, ugly. One direction. Which means I'm supposed to speed up completely to give you this, as you saw in one of my demo just now. Right? Dibasic, it means that one of these, in very local way, one of these gives two of this. Nitric acid is also a strong acid, but it is monobasic. So you guys should know that nitric acid looks like this. If you are doing this chapter, you should know that it looks like this, right? It produces this and this. One only, because it only has one, right? It'll be strange if I can get two out of it, right? Okay, ethanoic acid. Now this is the slightly trickier one, which you might not encounter in the syllabus. You look at this. This is actually the dissociation equation for ethanoic acid. Okay, don't be overly concerned about why it looks like that, because that will be explained in organic chem, which is like Sec 4 topic, right? Just appreciate two things. Number one, if I say it's monobasic, I should expect one H plus to appear, because that one H plus will then react with one OH. That's how it works, right? And it's weak. Second thing I want you to draw reference to is that it's weak. So number one, monobasic. Number two is weak. The weak refers to this arrow, reversible arrow. Okay, this may not be the first time you are seeing a double-headed reversible arrow. What is it? What does it mean? What does this actually mean? Let's say A plus B gives you products, for instance. Okay, if it's a reversible arrow, what it actually means is that every time A and B react together to form products in the forward reaction, so this is my forward reaction, at the same time, some products are decomposing back to give A and B. This is my backward reaction. So both reactions are occurring at the same time. They might not be occurring at the same rate, but they are occurring. This means that I'll never have 100% conversion, because every time I go to a high amount of conversion, some products start to break down and form back my reactants. So it's a back and forth thing. You will never get 100% yield. It's not possible, right? So right here, less than 100% yield, for sure. And that is a hallmark of weak acid and a weak base, which we'll talk about later. Yep. Okay, one small thing here, right, is stepwise dissociation. Okay, you will realize that acids, they are dibasic, tribasic, all these things. Actually, how the dissociation works, is that the acid will dissociate one by one, which means it will give off one H first and form the ion. And in step 2, this ion that was formed previously, which is here, will give up another H plus to finally give 2 H plus in the solution. But for strong acids, right, since both of these things take place so quickly, right, overall it looks as though it's taking place at the same time. Okay, so for strong acids, you can't really tell the difference. So you just learn it as this, it's okay. But just recognize that dissociation of H plus takes place step by step. Which means if I give you a weak acid, like for example, you saw H3PO4 just now, phosphoric acid. If he has 3 H in his formula, each of the H will come out step by step, one by one. One H, then another H, then another H. Not all 3 will appear at the same time. Okay. For strong acids, it looks as though both are appearing at the same time because it's the dissociation is pretty good. Okay. Right. So let's go on to some very fundamental true-false questions and some very basic MCQs just to solidify knowledge. So if you want, you can pause the video now, okay, and resume once you're done with all the questions in this page. Right. So let's go. Okay, true-false questions. All acids must produce hydrogen ions in water. Is that true? Of course it is. That's why it's called acid, right? Ethanoic acid can dissociate in water to give 4H, not all 4. Remember that ethanoic acid we saw in the example just now, right? It was monobasic. So at the very most, 1 H plus, not 4. It looks as though there's 4 H, but we did say that not everything that has H must be acidic or must dissociate. So this is clearly false. Leading on to that, all substances that contain hydrogen atoms are acids. No, there are so many things that contain H out there that are not acids. Is water an acid? No, right? It's 2H. Is ammonia an acid? No. So this is false. Acids have pH value more than 7. You learn in Sec 2, Sec 1 is less than 7. So this is false as well. Acids can change the color of dry blue litmus paper. Okay, this is interesting. Look at the word dry here. Okay, just now we said that acids can only act as acids in water. It means the acidic properties actually only show up when they are dissolved in water. What if there is no water? Then it wouldn't work, of course. But if you think about it, this question is a bit vague, because are they saying that the acid is already in aqueous form? Or if it is, then it's fine, because the water comes from the fact that there is water inside the acid solution. Okay, but if I look at it, take it at face value, right? I see the word dry. No, probably not. It probably wouldn't work. Because let's say if I were to put a piece of paper, let's say litmus paper, blue litmus paper here, it's dry, no water on it. Then I just maybe pass it acidic gas, HCl. It's not acidic until there's water. HCl gas. Obviously, nothing will happen, right? But if I dip the dry blue litmus paper in a beaker of acid, then of course it will change color, because there's water in here already, right? Plus the acid. Okay, that's that. Okay, next one. Weak acids are non-conductors. No, they are conductors. They're just not very good conductors, because remember what we said. What do we need for conductivity? In this case, right, we have mobile ions. The only difference is that the weak acid has fewer mobile ions. It still has mobile ions, which means it still can conduct. So this is false. They are not non-conductors, right? Question 2. What does the term strong acid mean in relation to nitric acid? Strong acid means fully ionized. This is my answer. Okay, in fact, the moment you see the word strong, you zoom in to the fully ionized. You got your answer already. The answer is B. Question 3. The strength of an acid is determined by. Actually, if you were listening, right? It's actually just this one. The degree of dissociation. In other words, what is the extent of dissociation? How well does it split up? Does it split up properly? 100%? If 100%, yes, it's strong. If not 100%, weak, that kind of thing. So actually only one. Only A, right? Concentration doesn't work, because just because the acid is concentration, right, does not mean that it is strong, right? There's no relation there either, which we'll talk about later. This one, number of H plus produced per molecule, it doesn't make sense either, because, for example, this guy can produce up to 3H plus per formula unit, per formula of the acid, but each of these dissociation is poor, so it is still considered a weak acid. So A is the best answer. It's the only answer, in fact. Question 4. When hydrogen chloride is bubbled into metabenzene solvent, pH is neutral. What could be the reason? Maybe you realize that metabenzene is actually an organic solvent. So let me write it here. This is an organic solvent. And we keep mentioning that acids only act as acids in water. What if it's not water? What if the solvent is not water? Obviously, then no dissociation will occur. It wouldn't even act as an acid, won't behave as an acid. So the answer is B. In this solvent, it won't dissociate. If it won't dissociate, then there's no H plus. Because by right, it's supposed to do this. But in this solvent, right, this doesn't occur. Question 5. These two acids are considered both weak acids. Let me highlight this word, weak acid. However, one's acidity is less than the other, which is always correct. Okay. Acidity, in this case, right, is talking about strength. So if I want to talk about strength, I need to talk about dissociation, right? So perhaps this question will make you realize that there are many types of weak acids out there. There are weak acids that can dissociate to give 1% H plus, some dissociate to give 0.1%, 0.001%. There is a gradient as to how weak can a weak acid go. Yeah. So if I look at the answer, right, surely you can tell me it's B. Because even though they are both weak acids, nitrous acid can dissociate to a bigger extent than acetic acid. Okay. Acetic acid is actually ethanoic acid. It's the same thing. Just a trade name for it. Okay, just FYI. So the one that dissociates to a greater extent will be slightly stronger because that's what strength is about, right? Dissociation. Okay, that's that. Question 6. Okay, following statements about dilute sulfuric acid are all correct. Which one confirms the acidic nature of the solution? Okay, I want to zoom in on this. Because what this question is saying is that all these 4 things are correct statements, but which one tells you that it's acid? Something like that. Right. Let's look at 1. PBT formed when aqueous barium chloride is added. This is true. I mean, the question says it's true. And I know it's true because I know that you will form barium sulfate, which you have learned before, it's insoluble. So this is true. But does it tell you that it's acid? No, not at all. Because as long as there's a sulfate somewhere, when I hit it with the acid, with the barium, it will react. It will form a PBT. That sulfate need not be an acid. It could be sodium sulfate. Yeah, that will also give you the same result. What about 2? Solution turns anhydrous copper sulfate from white to blue. If you recall, right, this observation here, right, is the test for water. Which means if there is water, I drop it into anhydrous copper sulfate, which is white, it will turn blue straight away. This statement only proves that there is water in acid. But does it prove that the acid is acidic? No. So this one already. Okay, how about 3? 3 definitely. Because I add UI, universal indicator, the pH is less than 7. It is true. All acids less than 7. This is true. It shows you that yes, it is acidic. What about 4? Okay, 4, perhaps if you already learn your acids and bases, you will realize that copper oxide is a base. The solution is able to react with base to form a blue solution because acids can react with bases, right? So this actually also confirms that this is acidic. Because actually very few things react with bases. Acids are one of them, right? So answer is D. Okay, so I mean, if you are not very convinced, like 4 is a bit strange. Like what does that mean even? All you need to do is eliminate 1 and 2, right? And you can get an answer already, right? Because everything here, there's 1 and 2 are all wrong, right? Okay, so that's that. Okay, question 7, which is the last MCQ here before the next section. Weak acid 1 mole, 1 DMQ of water. Even if you don't take mole, you don't know what this mole thing is all about. That's fine. Remember what we said, we can just pretend we're talking about 1,000 molecules, right? If I have 1,000 molecules of HX, if it's a weak acid, okay, so that means this arrow must be reversible. Out of 1,000, perhaps let's say 1% can dissociate. That means out of 1,000, right? Maybe only 10 comes out. 10 of them break up. Means out of this 1,000, right? 990 remain undissociated. So which graph looks the best out of the 4? Surely if you can follow my working, you realize that majority of it, right, should remain undissociated. And only a little bit of it comes out as dissociated. And my answer is A for this. Okay, so these are pretty fundamental questions for acids, just an introduction to acids. So hope that was useful for you. Okay, let's move on. Okay, I briefly mentioned about how concentration and strength are not related to each other. So in this section, right, we'll really talk about it. Concentration versus strength. Like I said before, just because an acid is concentrated, it doesn't mean it is strong. They are not related to each other. Yes. So look at this diagram. You can see that for let's say for example, if it's strong acid, at all concentrations, right, a strong acid will always completely dissociate. So you look at this graph, this diagram, the green balls and the white balls, right? So originally the acid was like that. Okay, one green. Okay, I don't have green color. Let me get green color. Okay, yeah. Originally, the acid looked like that. No matter whether the acid is concentrated or diluted, it should, however much acid is inside the solution, should split up completely. Okay, so that's actually the nature of the acid itself. So let me write here. The strength of acid is dependent on the nature of the acid itself. Okay, what nature are we talking about? Okay, that is beyond the scope of this topic. But it's like if I tell you it's sulfuric acid, because it is sulfuric acid, it is strong. That kind of thing. Okay. Looking at the other side, for weak acid, at whatever concentration, it will always be weak. It will always have partial dissociation. So you look at the top, this one. Oh, how many? Maybe 10 or 11. Only one comes out dissociated. So this one may be even worse. Maybe you can't even see the dissociation. It's so poor that I can't even see the dissociation, right? But by right, if I want to be very specific about it, I should put a blue, green dot and then a white dot. Let me just do this. So at any instance, right, what this diagram is trying to prove is that a weak acid is always weak regardless of concentration. So it depends on the acid itself, right? So again, concentration versus strength, they are not related to each other. Okay, if you have already learned more concept in stoichio, this bit is relevant to you. If you have not, then it's probably not that relevant yet. Yeah, but it's good to get a feel of it first. So again, if you talk about neutralization, if I give you a certain amount of acid, let's say I give you a conical flask full of acid, I tell you, okay, there is this concentration, maybe let's say it's in this case, let's say it's 1 mole per dm cube, and I have 50 cm cube, for instance. What this information tells us, even if you don't learn more, that means I'm telling you that, okay, this particular conical flask full of acid has a particular concentration and a particular volume. I'm telling you that within this acid, there is X amount of acid. If I have X amount of acid, going by mole rate, going by the reaction between acid and alkali, you'll find that I will need a certain amount of alkali to react it, to neutralize it, right? I don't care whether the acid is strong or weak, right? Because you cannot be under this misconception that, oh, acid is weak. If it's weak, right, it means I need less alkali to neutralize it. Actually, no, it is the same amount, right? Because it depends on the basicity of the acid. It's not about strength. So this, the rest of this page, right, tells you that, okay, if I have one more of strong or weak acid, I don't care if it's strong or weak, as long as it's acid and I know it's monobasic, confirm you will only require one more of NaOH to neutralize. Okay, so if this part confuses you because you haven't learned more yet, don't worry. When we teach you more in term 2, okay, this bit will become understandable again. Yep. Okay, let's move on. Okay, some more questions. Okay, feel free to pause the video. Okay, let's go. Let's move on. A weak acid H2A is dissolved in water. Which statement is correct? Correct. Okay, it is weak and it is dibasic. Can you see this part here? It probably tells you that it is dibasic. 2H inside is able to dissociate twice, probably. Okay, which statement is correct? Let's look at A. The solution does not contain OH ions is wrong. Because I don't want you all to be under this misconception that acids only got H plus, no OH minus. It's not true. There is some OH, but there's a lot more H plus than OH. That's why the thing is acidic. So no. Not to mention there's water inside. Okay. B might seem correct at the start, but actually it's wrong. Because this statement is telling you that there are twice as many of this as this present. Okay? That might not be true. Because number one, the dissociation is poor. Okay, number two, what makes you think that you dissociate completely either? Like maybe I just look at H2A, right? The formula like that. Does it mean that it must give me that? Okay, not entirely. Right? What if it did this? And then it stops because the second dissociation is too difficult for some reason. Okay, so this is like a KIV. Like I'm not very sure. Maybe it's an answer, But is there a better answer at the bottom? Okay, let's look at D. D is clearly wrong again because it's saying that the solution does not conduct. It does conduct, not that well, right? Because it does have some mobile ions, which means it does conduct for sure. The answer is C. Because if it is a weak acid, it means that a large majority of the H2A is undissociated, all right here. If it's undissociated, doesn't that mean that there's a high concentration of the original acid left in the water? C is the best answer. Okay, so between B and C, C is definitely much better. B is like a ambiguous, like, I don't know, but C definitely is correct. Yeah. Question 2, weak acid is dissolved. Which statement does not describe a property of this weak acid in solution? Okay. Does it form a salt with NaOH? Sure, it does, because it's an acid-alkali reaction. So this is a true statement, because this is acid plus alkali. To give salt and water, salt and water, salt and water. It's a true statement, which is not my answer. Let's look at let's see. C. It is partially dissociated. It's true. This is true. Because it's a weak acid, because we said weak already. Number 1, they say weak here. Number 2, they give you the arrow. So double telling you that, hey, this is weak. So that's not my answer either, because this is a true statement. It reacts with sodium carbonate to give carbon dioxide. If you learn acids and bases already, and this is a revision for you, you definitely know that this is true, because acids plus carbonate must give you carbonate, spell wrongly, must give you CO2, salt, and water. It's a must, right? So this is a true statement as well. Cannot make it. That's not my answer. Answer is B. Because we just said that don't care whether it's monobasic, don't care if it's strong or weak, as long as the basicity is there. Whether or not it's HCl or HX, as long as they're the same basicity, both are monobasic, I will require the same amount of alkali to neutralize, because that depends on the basicity, not the strength. Okay, if you haven't done more and you encounter a question like that, all you gotta do is eliminate the 3. Because the other 3, A, C, and D, right, are definitely true statements, which you already know. B is the only one that sounds a bit weird. That's your answer. Okay. Question 3 is an open-ended question a little bit. Which acid has a higher pH? Use the data and explain your answer. So if you look at this thing, you can clearly see that one takes much longer to react with the magnesium. One conducts poorly, more poorly, okay, quite poorly. So clearly acid Y is the weak acid. And you got to explain your answer. Okay, so it only partially dissociates to give a small amount of ions, which is why it doesn't conduct properly, right? Its conductivity is poor, because we said conductivity requires mobile charge carriers. It has, but very little. So let's say that. We'll say, okay, partially ionizes or dissociates. Let me write out. Dissociates to produce a low concentration of ions, okay, which act as mobile charge carriers. So a small amount of mobile charge carriers means that it is poor conductivity. So what else? What about the reaction? Okay, because the concentration of H plus is low, because it's a weak acid, it dissociates partially. So of course, it means that the acid Y will take a longer time to react. There's less H plus in the solution. Yep. Something like that. Yep. Okay, now let's move on to the next section. These are chemical properties of acids. If you don't already know this, okay, it's a good time for you to revise. Acids react 3 major ways. Number 1, metal, reactive metal. Number 2, carbonate. Number 3, alkali or base. 3 major reactions. Okay, let's go through it. First one, magnesium plus sulfuric acid gives you magnesium sulfate as H2 gas. Let's come up with the equation for that. Magnesium is a solid. We just saw sulfuric acid is aqueous, sorry. It gives you magnesium sulfate and H2 gas. It should be balanced already. Okay, so do this practice by yourself quickly. Ionic equation. If you guys can remember ionic equation, okay. If you are not very good at ionic equation, please pay attention to this particular section. So I'm going to do it once. And I'm going to show you how I come up with the ionic equation. How do I convert a full equation into an ionic equation? So let's use some empty spot. Okay. First things first. Some rules to follow, right? If it's SLG, for those in my class, I like to always do this. Solid, liquid, gas, or covalent. No ions. What does that mean? It means that if I show you something is solid or liquid or gas and it's not ionic, it's covalent, high chance that that particular substance cannot dissociate into its ions, right? It will remain as is in the ionic equation. That's one. Number two, this means that anything that's aqueous and aqueous ionic can dissociate. Means you can break them up into the ions. Number three, I need to cancel out the spectator ions. What are spectator ions? In fact, if you ask me this, right, you need to understand what's the point of the ionic equation. Yes, it's simply about me trying to find out what exactly reacts. Right? Although on paper it looks very nice, right? Mg plus acid, salt, and H2, but does everything react? What are the main substances that take part in the reaction and what didn't? Because if there are so many things reacting, it's so many substances in my equation, I want to zoom in to the actual reactions. So later, if I want to manipulate the reaction or anything, I can focus on these things. So to put this in perspective, let's just go through the motion and thought process first. Mg is solid. It's just a metal element. It has no ions. So let's leave it. Let's rewrite it as this. Sulfuric acid can dissociate into these ions, right? Because it's one of those very strange covalent compounds that can do this. So let me write it out. The mole must be the same because I must tell you that this is dibasic. One H2SO4 must give you 2H plus and 1 sulfate. It is a must. Okay? If you balance it here, right, you will not run into problems later. Okay? What about magnesium sulfate? It can break up. It's an aqueous ionic compound. It is soluble in water. That's why the state symbol is there. It's aqueous. Finally, H2 has no ions because it's a simple covalent gas. Nothing there. Okay. When I say spectator ions, the spectator ions, right? The word spectator here means that it's sort of looking, right, observing the reaction, like eye power only, just looking at it, not doing much. Which means if you look at this equation, doesn't it make it obvious to you that the sulfate seems to not be doing anything at all? It's simply sort of shifting its position from the acid to the salt to the magnesium. It's not doing anything. Which means, right, if I were to try to, let's say, I want to change the rate of reaction, I want to make reaction go faster. I cannot target the sulfate because sulfate is useless to me. It's not doing anything. Even if I change the sulfate concentration or whatever, right, it wouldn't make a difference. What's actually truly reacting, what is actually taking part in the reaction is your Mg and your H plus ions, which means my spectator ions are a distraction. They are distracting me from the true things that are actually reacting. I don't want them in my equation. That's why point 3 says cancel spectator ions. I cancel them out. I don't want them. Whatever is left behind, this chunk is your ionic equation. Okay. So if you have done the practice on balancing equation some time ago, right? Okay, look through the worksheet that we have, a lot of practices for you. See where the thought process comes from and how you can further do it quickly and accurately, which is why there's also a fourth one. Fourth one is balance everything. But I need to tell you that if you have already balanced at the start, then you need to worry. It will confirm be balanced later. If you fail to balance properly at the start, then you run into problems much later. Okay, so we cannot emphasize how important a balanced equation is. Okay, moving on. Carbonate plus acid gives you salt, water, carbon dioxide gas. So zinc nitrate, please remember the formula. It is all nitrates are soluble, carbon dioxide gas, and water. So can you see the state symbols are pretty important because once I give you the state symbols, right, I'm hinting to you what kind of thought process you must come up with, right, for creating and converting it into the ionic equation. So I'm just going to give you the ionic equation. Okay, you can figure out for yourself how did this come about. Okay? you will realize that in this example, right, this particular equation, your nitrates are your spectators. So they are gone. They're totally not there in the equation at all. The third one is the most simple one, most straightforward. Acid plus base gives salt and water. So in this case, NaOH plus HCl gives you NaCl aqueous, because all one compounds are soluble in water and water. The ion equation looks like this. Neutralization. Right. I think this is pretty straightforward. Okay. Moving on. Okay, so a few exercises. Okay, try them now. If you want to pause the video, please do so. I'm going to go through all of them. Right. Okay, let's do it quickly. Calcium plus hydrochloric acid gives you salt and water, salt and H2, right? So the salt is calcium chloride and H2 gas. Balance it, please. Put 2 in front of the HCl. The ion equation for this and that's it. Okay, next one. Copper carbonate plus sulfuric acid gives you salt, water, and carbon dioxide. Full chemical equation. Hopefully it's balanced already. Yeah, it's balanced already. Okay. Ionic equation. Hopefully you can remember this from just now. We did this almost identical question. Ionic equation. Sulfate is the spectator. Next one. Okay. MgOH2 if it's aqueous. Nitric acid aqueous. MgNO3 2 aqueous plus water, salt water neutralization reaction. Ionic equation looks like this. Okay, as you're doing this question, right, you will realize that at some point you cancel, you might end up with this. Please simplify it, because the entire thing can divide by 2. This is actually what they're looking for. Okay. Okay, let's continue. Actually, if you think about it, right, you keep doing a lot of those acid plus alkali, alkali plus acid neutralization reaction to give salt and water. If you do it too many times, right, the ionic equation conversion, you will start to realize a pattern that all of them, right, look like this. All of them actually, right? So of course, we wouldn't encourage you to skip steps and that, oh, just memorize that it's like that. Okay, we wouldn't encourage it. But of course, in a pinch, if you're running short of time, okay, you will definitely be able to zoom in to the answer straight away. But of course, the disclaimer here is this only works for acid and alkali because of certain conditions and solubility conditions that they have. Because if it is acid plus base, and if the base is not soluble in water, right, this thing doesn't work already. Okay, the ion equation will be a totally different thing. So please be very careful. Which of the following does not react with hydrochloric acid? This is a base. It does react. This is a metal, of course. Of course, it does react. This is also a base. It does react. The one that doesn't react is C. Okay, because right, we need to tell you that if I give you HCl plus MgNO3 2, everything is soluble, isn't it? Okay, let me balance it first. What would you expect to see if I add them together? Am I supposed to get this? Are the ions supposed to just swap positions and then, oh yes, I'm done? Okay. What you might not realize, right, is that if these two things are in the same container, let's say they're in the same beaker. Let's say at start, the ionic compound MgNO3 started off with just this thing floating around in aqueous form. I'm not going to add HCl into the solution. And then these two things, right, are also soluble in water. So when I put them in water, right, they will dissociate. So what I end up getting, right, is just a mixture containing 4 different types of ions, right, that will continuously bump into each other, dissociate, bump, dissociate. So they don't actually react at all. This is what I like to call ion soup. Okay, don't quote me on this because you can't use the word ion soup in exams. Just recognize that it's just a mess, just a mixture of some ions floating around, hitting each other, not doing anything. So there is no point in this. This is not even a reaction. You can further evidence this, right? If I ask you to find the ionic equation for this. There is no ionic equation for this. Everything cancels out with everything else, right? If there's no ionic equation, it means that there's no reaction. Nothing is actually happening here. 0. So C is the one that clearly doesn't work. Okay? Question 4. Which reaction is the acid not behaving like an acid? Acids must react with base, carbonate, or metal to form. It depends on what it does. So acid plus base gives you salt and water. Now, this is true. It is behaving, it's doing its job as expected. Let's look at C. Acid plus base, salt and water. Correct. As expected. D. Metal plus acid gives you salt and H2 gas. It is doing its job. B is the weird one because acid plus this thing becomes 2 other things, which falls outside of what you know acids can do. So this is hinting to you that, hey, perhaps the role of the acid here is not an acid, just a reactant to perform another type of reaction. So that's what they're looking for. That's what they mean by, say, not behaving as an acid. Okay. Question 5. Okay, question 5 is a bit of a trick question, but if you know what you're looking for, I'd say it's very obvious. If you go back to the top of the notes about reactions of acids with things, you'll find that the word is reactive metals. Reactive metals. If the metal is not reactive, it cannot react with the acid. The classic example is copper. Once you learn more about reactivity series and metals, right, you understand why copper doesn't react with acid, dilute acid. So if you look at this row of these four rows of things, you'll find that I cannot use this and this to form copper nitrate. I can use copper oxide, copper carbonate, but the copper metal itself cannot. So the answer is D. Yeah. Moving on. Dilute sulfuric acid reacts with copper oxide and copper carbonate. How are they alike? This is a base. This is a carbonate. Yes. How are they alike? Is it acid neutralized by alkali? No, it's not. Because one is a carbonate. Neither of them are alkalis actually. As both reactions proceed, pH decreases. pH actually increases because the acid is becoming not an acid, right? So just to put this in perspective, acid plus copper oxide, what does it become? It becomes this now. This is neutralization, isn't it? So the acid is becoming not an acid. So pH is not supposed to decrease in here, right? So nope. Both carbon dioxide liberated? Not really. There's no carbon dioxide here. Well, there is carbon dioxide in the carbonate reaction because it forms salt, water, and carbon dioxide. So not both, right? Not both. They're not like. But yes, both cases, water is a product. That is D. That's that. Okay, and that was that for acids. Okay, now let's talk about bases. For bases, right, and alkalis together, bases in general, right, they neutralize acids to produce salts. Usually that's what they do. And most bases you realize are insoluble. And if it's able to dissolve in water, it is called an alkali. And I'll tell you right now that bases generally are either metal oxides or metal hydroxides. Okay. So there are some metal hydroxides, there are many metal hydroxides that are insoluble in water, but those that can dissolve in water, base or hydroxide or whatever, they are called alkalis. Okay. So alkali is a substance that dissolves in water to give OH minus ions. Okay. So we probably have seen this before. this Venn diagram, I guess, right? Okay, let me see, where are we? Okay, Venn diagram. So it says that all alkalis are bases, but not all bases are alkalis, because the one in gray is the set of all bases that exist. Within that set, there's a small complete subset that can dissolve to form alkalis, right? So all alkalis are bases, but not all bases are alkalis. Okay, hope this part makes sense. Going back to just a little bit, you find that NaOH as a soluble compound, you put it in water, it does form Na plus and OH minus, and that is what an alkali is. Alkali must give OH. In the same vein, like how acids must give H plus, alkalis must give OH minus, must. But bases, no need lah, because if they're not soluble, then they can't even give OH. They're not soluble, right? Okay, so there are a few of them. So you can see there's a small star, right, at aqueous ammonia. So for those who sit in our classes, especially for IP, your teacher might teach you that this doesn't really exist, right? Because what we learn later, the more formal definition, I guess, reaction of ammonia with water is that it reacts directly to form this. There is no intermediate ammonium hydroxide that later dissociates. So it doesn't do this. It doesn't form this first, and then in a roundabout way form this later. It doesn't do that. So this entire chunk is actually, technically, it's wrong. But of course, if your school is okay with it, then we suggest that you follow your school. But this is the formal one, right? Okay. So that's why aqueous ammonia, there's a star there. Just take note of that. Okay? So you can clearly see, right, that there's something about basicity here as well. Okay. Or rather acidity. Okay, let's see. Okay, before that. Turns blue litmus paper, red litmus paper blue, sorry. Because it's alkali. Able to conduct due to presence of mobile ions. Definitely. Okay, and look at this. Now the terminology will make more sense to you. So if an acid is monobasic, it means that the acid reacts with a base. Therefore, a base is monoacidic because it reacts with acids, right? But of course, if you don't want to concern yourself with all that terminology, right, just focus on the one and the two, the mono and the di. So you can see on top, right, clearly that NaOH is monoacidic. But if you are not very familiar with this, like your school never tell you monoacidic as a phrase to learn, just remember that the mono here means that it can give off one. Mono, this is di for sure. This is also mono. Okay? What's one of this? Can give one of this. Yep. Okay. Strength of alkalis and strength of acids are actually pretty similar to each other. Most hydroxides that you learn, most alkalis that you learn in school, they are strong, with one exception. And the exception is aqueous ammonia. So you saw me doing this just now, right? In the equation in the previous page, I did this. Instinctively, I already give you this reversible arrow, which implies that aqueous ammonia is a weak base, weak alkali in this case. So it's the only one that's weak. So the dissociation equation, okay, just rewrite it. Remember, it looks like this. Okay, and it's its symbols. This is a gas, this is liquid, this is aqueous because ions are aqueous, right? NaOH, because it says strong mono, one only, complete dissociation, aqueous, aqueous, aqueous. Okay, KOH is exactly the same because it's mono and strong. State symbols are the same as the previous one. Barium is also strong. Like that. Yep. Okay, let's do quick test. Okay, true, false. Metallic oxides and hydroxides are bases. Yep, that's true. All of them are. Okay. All bases contain hydroxide ions. It's false because some bases are metal oxides that are insoluble. So let's say, for example, right, let's see, what can I think of? Copper oxide. It's a base, yes, but it doesn't dissolve. If it doesn't dissolve, it cannot give you OH minus, which means this statement is false. Alkalis have pH values greater than 7. Yes, they are alkalis That means they are already hinting to you that it is a soluble, it's aqueous form already. You put a pH meter or whatever, universal indicator, definitely greater than 7. Okay, the greater the pH values, the greater the concentration of hydroxide ions in water is true, because that's what it means, right? Because we said if there's more H+, it's a stronger acid. Means more dissociation, stronger acid. It means that if there's more H, it's a stronger base. Oh, not strength, stronger base. Okay, stronger base. So this is true. Okay, ammonia ionizes fully in water to produce OH. No, that's not true, because we established that ammonia is weak base. So the word fully here is offensive to me. So no. Sodium oxide has a properties where alkali is false. It is a base because it's a solid sodium oxide. It looks like this, by the way. Oops. It is only an alkali, right? After you add water to it. Before you add water to it, it's just a base, just like that, Na2O. So this is false. A bit tricky, but this is false. For bases and alkalis reaction, it's a little bit fewer than acid reactions, because the first one, we already, the second one, sorry, we already know this one. Let's do this first. Bases can react acids. First, just now we said acids react with bases, right? Now we say bases react with acids. It's the same thing, actually. So just to go through the motions of how they could react, we saw it earlier. Barium hydroxide plus hydrochloric acid gives you this and this. That's it. Neutralization reaction, luckily, is acid and base. Acid and alkali. I straight away give you this. Sulfuric acid plus copper oxide. Okay, it's a base. This is not alkali now. This is a base. Now let me just write it here in case you forgot. This is a base. Oh, this is a base. The full equation, sulfuric acid plus base gives you salt and water. Ionic equation. Okay, if you follow the rules that we did just now, you realize that it looks a bit different now. It is not what we just saw for the H+ OH-. It looks like this. Okay. Try it out for yourself. See if you can actually get to this point by following the rules that we just talked about. And that's for acids and alkalis, acids and bases. This is the one that is very unique to alkalis and bases. More alkalis than bases, actually. Unique. It doesn't come out often, but when it does, you must know what it is. Right? So all bases and alkalis, right, can react with ammonium salts to produce salt, ammonia gas, and water. Ammonium salts are salts that contain the ammonium ion. This one. Yes. Right. So let's look at one first. Okay, this one is a base. Plus ammonia. Okay, let's look at this first. Sorry. This one is a base. Alkali. Ammonium salt gives you salt, water, and ammonia gas. Okay, so this one only works for ammonium salts, right? So that's that. So let's give you an example of how a base could react with ammonium salt. This is ammonium nitrate. It forms calcium nitrate plus ammonia plus H2O. So that's that. Okay, nothing much here. And don't need to worry about the ionic equations for this, because it's usually they won't usually test you about ionic equations for bases, more of alkalis. So this is pretty important. Please know how to get to this point. Okay, let's move on. Which of the following is a characteristic property of alkalis in aqueous solutions? In aqueous solutions means I already say alkali, and I keep double confirm it is aqueous. It is already dissolved in water. So this is wrong. I mean, A is wrong because this is a characteristic of an acid. This is wrong because again, it's a characteristic of an acid. This is wrong because again, it's an acid reaction. This is the one we just talked about, ammonia gas. Yes. Question 2. Okay, KOH is a typical alkali. Give the name and the formula of the negatively charged ion present in actually all alkalis, right? If the alkalis, they are already dissolved in water, this is called a hydroxide ion. Okay, that's why it's called potassium hydroxide, because there's a hydroxide inside, right? And because it's an alkali, there are many properties, physical and chemical. So definitely, since it's dissolved, it has mobile charge carriers, so it conducts electricity for sure. What else? Because it says properties, right? They never say physical or chemical, so you can just give any. How about turn red moist, red litmus blue? It doesn't even need to be moist because there's water already. How about react with ammonium salts? Okay, so many properties. One similarity and difference between a base and an alkali. Both react with acids the same way, right? Water, okay, make it more complete via a neutralization reaction. That is a similarity because they both react the same way. The difference is that one is soluble and one is not necessarily soluble. So alkali is a soluble base, but not all bases are soluble. And so what am I saying? I'm saying that alkali confirms soluble. Some bases may not be soluble. Yeah. Hope this is fine. So let's look at D. How do I tell the difference between a carbonate and a hydroxide? Actually, quite easy. If you are following properly, right? All I need is, all I'm saying is that I have maybe a test tube that contains a certain chemical. I don't know what it is. Is it KOH? Is it K2CO3? Okay, is it K2CO3 or is it KOH? Okay. In order to do that, right, we need to add something that gives a certain observation. One, if it's this, and two, if it's that. Okay, what do I mean? So let me just write down the answer first. To the solutions, to the solution. Okay, to solution, add an acid. Actually, any acid will work. But you might want to be more specific. Maybe add HNO3, nitric acid. If the solution shows effervescence of a gas, okay, it is probably this, because only carbonates can react with acids to produce CO2. If nothing happens, then it is not potassium carbonate. If solution remain colorless, okay, with no effervescence, then solution is KOH. Okay. Nothing much. Okay, so this kind of questions, right? I know it's very tempting to be like, maybe I go and try to use a litmus paper, that kind, right? Like, okay, maybe KOH is a strong base, then maybe potassium carbonate is a weak base. So if you use universal indicator, I can tell you apart. So firstly, this one very dangerous. They will tell you that it's alkaline. So if you use universal indicator, right, how would you know if the K2CO3 is weak base or not? You don't know. And number two, this kind of answering can be a bit lazy. That might not be what your teacher or your exam paper is looking for. They want you to prove to them you know what kind of chemical reactions, right, are occurring, right? Carbonate reaction with acid, but potassium hydroxide, you can't see anything. This is more value adding. That's very lazy to be like, oh, add indicator lah, everything add indicator. I will know. No, that's not a good answer. Yep. So try your best to use reactions and observations instead of using very simple things like indicators. Yep. Okay, moving on. Okay, so this page is just a summary of acid and bases. So nothing much. I won't go through it because this is just basically a point by point comparison between acids and alkalis. Everything we have done already. Just one small thing to talk about. Can you see this part here? Remember what we talked about? We talked about the stepwise dissociation. Oh, sorry. Stepwise dissociation of acids. Okay, but by extension, we'll talk about alkalis as well. But look at this, right? Can you see? H3PO4, phosphoric acid. Because it's a weak acid, right? The three dissociations are actually very slow. I can see them occurring. So you can see it dissociates to give one first, and then forms this salt. This ion will dissociate one more time, and then one more time. So 3 very distinct steps when it comes to dissociation. And again, this is ethanoic acid. Okay, don't need to worry yourself with which one, why does it look like that? How come only the H comes out from the back? No need. At this point, it's too early to learn about that. Okay? And remember what we said. In order for something to be acidic, it doesn't mean that it only has H plus and not OH minus. There is OH minus, but there's a lot more H plus than OH minus. So as long as the concentration of one number is bigger than the other, right, that is what it becomes. Like if more H plus than OH, it is acidic. If more OH than H plus, it is alkali. Things like that. Yep. Okay. Okay, we are going near, no, I won't say we're nearing the end, but okay. So let's look at measurement of pH. Okay, so we know already. I basically just described the whole thing to you just now. So it just basically talks about the relative concentration of H plus and OH in solution. Whichever is more, that's where it will be. So if there's more of this, then this, acidic. If there's more of this, then this, alkaline. So just maybe briefly remember the numbers. Like in general, strong acids are low pH 1 to 2, weak is like 3 to 6, that kind. And then strong alkalis are 13, 14, weak one is 8, 9, 10, that kind. So that's a range. There's a range for you to follow. And of course, neutral is 7, right? So, but don't be concerned with this yet. This square bracket, right, actually means concentration. So whenever you see square bracket, it refers to concentration. So instead of the guys writing concentration of H plus, it's actually H can write this. Okay, but that's not for you guys lah. That's for us to make the notes more concise. Anyway, so that nothing much here. Okay, color scheme. Please remember that for red, right, it's usually I think 1 to 2 around there. It's orange is maybe I would say 3 to 4. If it's a yellow, it's maybe around 5 to 6 around there. There's a range lah, of course, right? Okay, we talked about this already. Okay, for pH measurement. Okay, we are not going to dive into the formula for pH because that's a H2 chemistry kind of thing. But we just want to inform you all that pH is an actual direct measurement of the amount of H plus ions that can exist in the solution. So I'll say that, I won't say it's proportional, but it's directly influenced by, there's a calculation involved that tells you, right, based on a certain amount of acid, let's say maybe X amount of acid per DMK of solution. Based on this number, right, I can do a calculation and I can tell you what's the pH of that solution. So pH is not an arbitrary number. Like, oh, I see this acid, it looks like it's strong acid, let me give it 1, like that kind of thing. It's not like that. It's a bit more complicated than that, but we will not get into that today. We will not get into that for another few years, actually, right? So just be aware that the more H plus there is in the solution, the lower the pH, right? Because low pH means acidic, right? So I'll write here again, more, okay, this, okay, I'm using the square bracket, results in low pH. Conversely, right, if there's less of this, there's higher pH. Like that. But of course, less than 7, yeah, for this. Okay, moving on. Okay, this next portion here, right, is just one very small thing about fertilizers, because we do realize that calcium hydroxide, slick line, okay, this is calcium hydroxide, or right here, calcium hydroxide, is usually pretty good at neutralizing soil acidity. Let me highlight this in a different color. Soil acidity, because if your soil is too acidic, many plants cannot grow, right? But at the same time, plants also require nitrogen because they cannot synthesize their own nitrogen. They need to get nitrates from the soil. Nitrogen, nitrates, ammonium from the soil. They must get elemental nitrogen N from the soil, right? So if they can't get it from the soil, then how? We need to use fertilizers, right? Fertilizers that contain ammonium or nitrates, which are good. So for example, this few, pretty good. And the classic question is, can I, if I have a plot of land that has acidic soil, and I also want to fertilize it, can I put them two together? Is there any special considerations if I were to against putting an alkali and an ammonium fertilizer together? You can't. The answer is never. You can't do it. Why? Not because it's dangerous, but because this fella here is an alkali, and this guy is an ammonium salt. And what did we just learn? Ammonium salts react with alkalis to form salt, water, and most importantly, ammonia gas. So that means to say, if I give you a plot of land that needs both things at the same time, if I add two things at the same time together, they will react with each other. Is that a bad thing? Not really, until you remember that the ammonia that comes out, right, flies off. It evaporates. It's a gas, right? It evaporates into the air. Then this means that your soil, right, has no nitrogen, because the nitrogen that was supposed to come from ammonium is now gone. Then what is the point of me doing this thing in these steps in the first place, right? So it will really deprive the plant of nitrogen, because I did it too quickly, I put it together. So these are some special considerations. Do take note. Questions will ask you things like that. Okay, moving on. Okay, what about the reaction between ammonia and dilute sulfuric acid is true? Okay, let me just go through one by one. A PVT is formed? Nope. Because the product, okay, this is ammonia, right? The product is probably ammonium sulfate. All ammonium compounds are soluble in water, right here. All ammonium compounds are soluble in water. If that is true, it's no PVT lah. Can it be used as a fertilizer? Yes, it can. Because we just said that, yeah, ammonium salts are pretty good fertilizers. Is ammonia gas released? No. It's only released when ammonium salts react with alkalis, as in this reaction. Why would ammonia react with acid to produce ammonia? That makes no sense, right? Can the product be used to treat excess acidity in the soil? No. This one is a job of alkali. There are no alkalis here. Answer can only be B. Next question. Okay, we are given two compounds X and Y. 1 mole of this gives 3 moles of ions equal solution. Okay, and one gives a gas that turns red, the blue litmus red, one turns red litmus blue. Okay. So even if you haven't learned more, that second statement, right, shouldn't be very scary to you. Because what this means? It means that if I have one, let's say, for example, if the thing is maybe X, for instance, it means that X, right, can dissolve in water to give 3 different ions, 3 non-different, 3 units of ions, 3 units of ions. One unit of this, 3 ions. Case in point, let's say, for example, I give you sodium carbonate. 1 of this, if I dissolve it in water, it can give you 2 of the sodium and 1 of the carbonate. This is what I mean by 3. 2 of this and 1 of this. In the same vein, sulfuric acid, when dissolved in water, is able to give me 2 of this and 1 of this. That is what I mean by 3. Okay, but of course, if you have taken more, if you have learned more already, then this will make even more sense to you, right? Okay, so what about the identity? X is clearly acidic because it turns blue litmus red, so X must be acidic. Y must be alkaline. Okay, no, not really. Yeah, Y must be alkaline because ammonium carbonate, X will react with the carbonate portion to give carbon dioxide. That's why it's acidic. It's the gas that's acidic. Y reacts with the ammonium portion. Oh, sorry, with the ammonium portion of the compound to give ammonia gas, which is alkali. So all we need is to tell me which one is the acid, which is alkali. So this is this one. B. Okay, question 3. Complete the table by giving the formula of ammonium phosphate and naming the compound NH4NO3. So this one, ammonium's formula is this. I mean ammonium NH4 plus, right? Phosphate, if you saw just now, it looks like this. So if you do a crisscross method, since this is an ionic compound, do a crisscross method, you will be able to get something like this. NH4 PO4. As for NH4NOH, this is ammonium nitrate. So this is literally ammonium nitrate. Is that okay? Okay, part B is a constructing balancing equation. This is quite fun. Urea, which is this guy here, CONH2. Oh, okay, there's typo. Okay, now urea is not this. Urea is this, CONH2. Yeah, so change that in your worksheet. Okay. It reacts with water, just totally in water to produce ammonia and a gas that forms a white PBT in the water. And of course, the gas is carbon dioxide. Right, balanced chemical equation and state symbols are not required. So all we got to do is to look at this thing and think of how to balance. Quite simple. Done. Yeah. What is the main reason for adding hydrated lime to soil? Of course, just mentioned that it is to neutralize excess acidity in the soil. That is the whole purpose of adding a base or alkali to an acidic soil, right? And just to recap, why should these two things not be added to the soil at the same time? One is an ammonium salt. One is alkali. You can't do that together. We just mentioned. So let's just put it into words, proper words. Okay, we will say the ammonium ion in ammonium phosphate will react with the hydroxide ion from lime, from the hydrated lime, from the lime to liberate, to liberate ammonia gas, which then escapes into the air, thus depriving the plant of nitrogen, which is essential for growth. Yeah. Okay, something like that. This will be about 2 marks worth. Okay, this is just me being a little bit more specific. So I'm actually telling the person, I actually know what is the actual reaction. Because if you break down this reaction to the bare bones, right, it is the ionic equation is literally just the ammonium and the hydroxide. Okay, but if you don't want to, you can just say that ammonium phosphate will react with that COH2 to produce ammonia gas, which is here. Then this the last part is the same. Yeah. Is that okay? Let's move on. For oxides, okay, this is the next thing. Oxides can be classified into many things. Okay, I'm sure you know that already. Firstly, let's classify oxides. Oxides means compounds that contain O, so like contain this O2 minus oxides. Firstly, they can be broken down into 2, metal oxides and non-metal oxides. Further broken down into 2 more categories. Most metal oxides are basic, most. Such as, let's give a few. This one, this one, this one. What else? Okay, actually a lot. Okay, maybe even this. Why not? Most non-metal oxides are acidic. For instance, a few. But there are exceptions. Some of them are amphoteric. Some metal oxides are amphoteric. In your syllabus, there are 3 of them. The acronym is ZAP. What does amphoteric mean? Amphoteric at the bottom of the page, it means it can react with both acids and bases. Means it displays properties of both acids and bases, which makes them very unique. They can react with both. The ZAP here refers to zinc oxide, aluminium oxide, and lead-2 oxide. So lead-2 oxide. These are the 3 exceptions. For neutral oxides, for non-metals, right, they are neutral in the sense that they don't react with anything, not acids, not bases. So this one, you cannot know nitrogen monoxide, carbon monoxide. Water is oxide, right? It's an oxide. And one more. How about this one? Okay, this one not really in syllabus, but good to know that there are a few more out there. This is extra. Yeah. Okay, moving on. Let's try some questions. When dissolved in water, the solution containing the oxide turns blue litmus fluid. Okay, what is this? oxide. Okay, it is to remove unwanted smell of vinegar, blah blah blah. So it's blue litmus red means the oxide must be acidic. Clearly, it is a non-metal oxide. Yes. If you saw the previous page, which means not this. Number 2, this is neutral. Answer is C. This is sulfur trioxide. Okay. Next one. Metal oxide dissolves in water. Metal oxide. Metal oxides are basic. If the basic oxide is able to dissolve in water, it forms an alkali, which means it is this one. Yeah. Okay, not really blue because there are not that many metal oxides out there that can dissolve. The most notable ones, right, are your group 1 metal oxides, which means your sodium oxide, your lithium oxide, your potassium oxide. These are the ones that when they dissolve, right, they give strong alkalis. That's why the color I'm looking at, right, is violet rather than blue. Which ones can form neutral oxides? Only non-metals can do that, which means straight away zoom into carbon. Sulfur cannot. There's no such thing as sulfur monoxide, if you're wondering. This guy is acidic, this guy is acidic, blah, blah, blah. Not possible. Only carbon can because of carbon monoxide. Yeah, these two just out already. Yeah. Okay, question 4. So I'll have a mixture of gases that bubbles through a bunch of substances, acid, sulfuric acid, and sodium hydroxide. If I only get one gas at the end, means the other gases, right, either reacted or dissolved into the different containers. So what could the mixture of gases be? Let's go through all the options. It cannot be A, because this guy is a base. This guy is acidic. This guy is acidic. Halfway through, right, surely they'll all get reacted because there's an acid here and a base here. Surely. So that's not the answer. B, this guy is a base. This guy is acidic. This guy is acidic. Okay. So that's not great either. This guy is acidic. This guy, okay, sure. This guy is neutral. So it probably wouldn't react with anything, right? And it's also not soluble in water. These two are not soluble in water. But I want one gas obtained at the end. I don't want two gases obtained at the end. So that C is also not my answer. My answer is D. Because this guy is neutral, so it will be collected. This guy is acidic, it will dissolve. This guy is basic, it will dissolve. Answer is D. Okay, hope that is okay. Okay, elements X, Y, Z are in the same period of the periodic table. What order do they appear in? Means left to right lah, order. If X forms an ionic oxide, sorry, Z forms an ionic oxide, it means it must be metal because metal oxides are ionic. So Z is probably on the left side of the periodic table. Solid Y doesn't conduct electricity, probably means that it's a non-metal. And non-metals are generally speaking, right, on the right-hand side of the periodic table, which is here. X forms amphoteric. If you look at the periodic table, right, zinc, aluminum, and lead are somewhere in the zinc, aluminum, lead are somewhere in the middle of the periodic table, right? So either one of this, which means X must be in the middle. My answer is Z, X, and Y in that order. Question 6, sorry. Element burn in air, dissolve in water, greater than 7, which means alkali. Which means it must be metal oxide, because metal oxide are basic, right? If metal oxides are basics, some of them can dissolve in water to form alkalis. So we look at metal oxides. This was gone case already. Between C and D, what's the better answer? Okay, I'll tell you that firstly I need to burn it in air first, right? This is combustion. So I need to form the oxide first. Means from here, if I react aluminum with oxygen, likely I will get this. Here, I will get this. Unfortunately for us, right, this guy is insoluble in water. So I can't even dissolve it in water. How do I get anything at pH greater than 7? So this is also not my answer. This one, yes. Because calcium oxide can dissolve in water. It forms this lime water, isn't it? Okay, but again, as we always warn you in class, right, this guy is sparingly soluble. So just be a bit careful when you see questions that relate to calcium hydroxide. So the answer is D. Question 7. Which of the following chemical reactions suggests that this fellow is amphoteric in nature? Okay, amphoteric means, right, it is supposed to be acting unlike itself. Okay, unlike what it's supposed to do. Let me give you an example. A is metal oxide plus acid gives you salt and water. That means this is a base. Yes. If that is a base, right, metal oxides tend to be basic in nature. So this A is not the answer because the metal oxide is behaving like a metal oxide. It is behaving like a base. That's not so good. Let's look at C. C is acid plus alkali give you salt and water. SO2 is a non-metal oxide, right? So it tends to be acidic. Is it behaving like an acid? Is it doing its job as an acid as expected? Yes. So that's not my answer either, because SO2 is behaving like SO2 should. Non-metal oxide, acidic. What about B? B is actually my answer. Why? Because this guy here is the alkali. This is salt and water, which implies to you that this is neutralization, which means this guy here should be acidic. Non-metal oxides are acidic, but indium, In, is a metal, which means this oxide, right, is a metallic oxide. Yet the metallic oxide is acting like an acid. Well, most metallic oxides are bases. This guy is acting not like itself, not like what it's supposed to. So it suggests that this guy could have amphoteric properties because it's doing opposite of what metal oxides can do. Yeah? I hope that part makes sense to you. Okay, question 8. Just fill in the blanks for all these things. Carbon monoxide is carbon monoxide, 1O only. Okay, the other oxide is carbon dioxide. It is neutral for carbon monoxide, we just learned that. Aluminium oxide is like that, and it's one of the 3 that are amphoteric. Okay, just a little bit more on this. One difference in the physical properties, only one physical. So things like reactions cannot make it. Only physical properties, such as what? MPBP, density, state, color, conductivity, all these things are metal properties. Physical properties. So there's so many, right? So I just need one. How about aluminum oxide has a high MP or BP, melting point, boiling point. Okay, while these ones are or not have low MPBP. There's so many boiling point, boiling point, density, color, state, etc. A lot of things. Okay, next one. Okay, another balancing equation. Aluminum oxide reacts with sulfuric acid to form aluminum sulfate and water. Give the balancing equation. I hope you realize that because of this, right, I can do a crisscross. Look at this. And once I'm done, I just need to balance it. Okay, aluminum is happy, sulfate is not happy. Put a 3 here. Now that I put a 3 here, right, I have to do it for the water as well. Do I need to say symbols? I need to say symbols. This guy is a solid. This guy is an acid. All sulfates are soluble except for a few. This is not one of them. And liquid. Okay. Next. Some common oxides are shown below. So choose one that fits the description we're looking for. An oxide that dissolves in water to form acid rain. So it must be a non-metal oxide that is acidic, right? Not neutral, acidic. So just need to choose one, and oxide, right? So this works. I guess this works. Solid oxide surely can. Want to use this one also can. Either one is fine. Part B. 2 oxides that are amphoteric. Yours is AP. Okay, 2 so I need both. Okay, this one and this one. An oxide that dissolves in water to form pH 14 means metal oxide basic. Metal oxide. Any more? Let's see. Okay. 2 oxides where the ratio is 1:1. Okay, there's so many of them, right? Carbon monoxide, copper oxide, calcium oxide. So many of them are 1:1. 2 oxides are likely to be gaseous. Generally speaking, your simple covalent non-metal oxides. Okay, any basic compound comes colored. Okay, this one may be a bit unfair to you because if you haven't learned much about QA and whatever and colors of ions, you might not know that certain things are colored. So never mind, I'm just going to give you the answer. This guy here, oh sorry, This guy is actually a black compound. When you put it in water, it forms copper sulfate, which is blue. So that's what they mean by colored compound. So the answer we're looking at is copper oxide. Last one, doesn't change either red or blue, which means it's neutral. Cannot react with either acids or bases. There's only one that can do that. Can? Okay. Okay, so moving on to the I think our last section on titrations. So this one, I think some schools, some of you may not have done this part yet, and some of you, even though you have learned this, you might not be tested for it. And because those people who have learned acid and bases but haven't learned mole concept, the questions that they can ask you can be a little bit limited. So over in this last section, right, we talk about I'm going to select the questions that more relevant to just a very generic titration kind of questions. No calculations involved. So that's okay, right? So for titration reactions, right, we usually deal with neutralization, because if you've done titration reactions in lab already, you will know how it looks like, right? And often there's a substance in a burette, there's substance in the pipette that goes into a flask, right? And then you do some titration. You unscrew the thing. Yeah, you unscrew the thing. You allow the liquid to flow dropwise. Blah blah blah. At the end of the day, you will get a salt solution in your flask, and you'll know when to stop because your indicator will change color, something like that. Yep. So we're going to talk about that. Titrations, right? Okay. By right, if you have the time, it should be the addition, drop by drop addition of one reactant to a fixed volume of another reactant. Okay, stoichiometric in this case means that the mole ratio, the amount of acid and bases, should be enough to cancel each other out to form only salt and water. No excess reagents remain at the end. Okay, so that's that. Okay, the rest of this page and the next few steps, right, are just for you to read to how to perform the titration. Okay, so I won't talk too much about it, but I'm going to draw out something here, the process. Hopefully my ugly sketches, right, can help you to visualize how you can actually perform the titration, right? Okay, so step one, I'm going to get a pipette. I think it looks like this. Pipette, okay, has a marking. A pipette can only put a fixed volume of liquid, yes. So there's always this orange ball called pipette filler or something. So you're going to pipette up a certain amount of liquid. I would say 25 cm cube of something. What does this experiment ask us to do? Okay, let's just use acid, okay? Let's use acid. Acid, maybe HCl. Okay, so it's filled up. Once this is done, I'm going to pour it into a conical flask. I'm going to pour into conical flask. Get my color out. Okay, I'm going to do it. Okay, here. Okay. So when in this particular flask, now I have 25 points. It's the same 25 cm cube of the acid. Next, I'm going to take a burette. How long should I draw it? Okay. It looks a bit like this with a screw cap at the end and some markings. Yes. I'm going to take burette. I'm going to fill it up, hopefully to the max, 50 cm cube with my base. Let me change color. What color should I use? Maybe blue. Okay. Just to differentiate the two. I'm going to fill it up to the max. In here, 50 cm cube of maybe NaOH. Okay. Haven't finished. I'm going to put some indicator inside. Okay, I'll talk about indicators later part of today. Okay, maybe with the indicator, maybe there's a color change. Okay, let's assume there's a color change. Maybe it changed to, I don't know, red, maybe. Now, I'm going to place this guy. Okay, never mind. Place this guy with 25 cm cube of acid underneath. Oops. Got space? Underneath my burette. And I'm going to start my titration. I'm going to unscrew the thing a little bit. Okay, some schools, I mean, if your burette is a bit all right, it's still the crocodile clip. Okay, whatever it is, you are able to slowly, drop by drop, add in the acid. Then the moment you add in, right, you must keep swirling, isn't it? You must keep swirling. When you keep swirling, right, you start to notice as you add more and more acid into the solution, the color starts to change slightly. You will keep adding drop by drop, preferably, until there's that one drop that changes the color permanently. And that's when you stop the reaction, isn't it? So perhaps at some point, maybe it was originally here, right? Maybe down to here. Okay. Then the thing change color. Let's see what color should it is. Maybe change to orange, maybe. I don't know. Okay, then I stop. After I stop, I will record this number. Like, what was the amount of NaOH that was used to cause this to reach this stage? Maybe, let's say maybe 15 cm3, maybe. Okay. And I'm going to repeat the whole experiment this time without the indicator. I'm going to do the whole thing again. This time around, the indicator is not there. Okay. I'm going to use my 15 cm3 exactly to pour into the acid. And at the end of the day, right, what is inside here? It should only contain exactly how much alkali I used to neutralize to form an exact amount of salt and water, and nothing else, preferably nothing else. Right. Later on, I take this thing, I can go and dry it, crystallize it, whatever. That is my salt solution already. And this is how titration works. Let's go through the motions again. Okay. Can see? Burette, pipette. This is what I drew. Hopefully the drawing helps you remember. So again, pipette can only put a fixed amount and an indicator. And then I got burette, and then I'm going to fill the base. And I let it drip, swirl it, like I said, swirl it, right? And then stop, and then there's a permanent color change. I'm going to repeat it without the thing, without the indicator, to ensure purity of the sample. Okay, so that's an experimental procedure. Unless you're doing salt prep, they wouldn't really ask you to list out the steps at this point, unless you're doing salt prep. That means you do titration, adding excess, precipitation, then yes, you need to remember the steps properly. Okay. Titration, of course, to how do I interpret the data, how do I collect the data? Yes. So this is called a titration curve. I can sort of see, right, if I plot certain axes, I can actually get more information out of the titration reaction. All titration curves, right, should follow this S shape that you see on screen. S shape, inverted S. The midpoint is called the equivalence point. Sometimes you know it as the endpoint. It is the same thing. Midpoint of the curve here. So if I drop down, right, vertically, right, that point here tells me exactly how much of the titrant from the burette that added to completely neutralize whatever was in the conical flask in the first place. Okay. So can you see the initial pH tells us whether acid or base is being titrated. Of course, this means that the acid is in the conical flask. I add base slowly. At one drop, the pH will shoot beyond 7. Right. Okay. So at the point I can stop already, because I know that this is the amount that's necessary for my reaction to be complete. If I flip it around, if initially my conical flask contains a strong base, so of course the pH will start at 13 or 12 or something. Then I'll titrate until I reach here. That one drop that causes the color change to go crazy, okay, and the pH to also go crazy. It just dives down to the acid. Okay, and then the mark here is me having added enough of the thing from the burette to neutralize it completely. Okay, and just an extra thing, there is a difference whether you use strong acid, strong base, or strong acid, weak base, or anything else. Okay, this is something extra because we are only required to figure out the shapes of the curves. Okay, you can either do it by memorizing, or you can try to understand in a very layman, informal way how it's supposed to work. So I'm going to show you how we will draw it. So let's look at the top left. If I start off with something, strong base, and I slowly add acid, which means the starting pH should be somewhere, I guess somewhere here, right? And add more acid. Since all the curves must follow this inverted S shape, right, you look a bit like this. Yes. This should correspond to the endpoint. And I should end off like super low because it's a strong acid. Means beyond that endpoint, right? Me spamming more acid, right, just makes the solution acidic, right? And it should reflect the acidic nature of the solution. How strong is it? If it's a strong acid weak base, okay, this one's a bit different. Weak base means, right, you start off the titration with the lower pH expected already, maybe somewhere here. And watch what I do. The graph sort of follows, oh, sorry, I think not so good. Let me draw it better. The graph sort of follows the same general shape. The only problem is, look at endpoint. Where is it now? It's not 7 anymore. It is somewhere here. Less than 7. So endpoint pH is less than 7. Of course, the best question is why? Why is it less than 7? Correct. At this point, right, it is not too much to teach you why exactly this happens. Okay, so we won't talk about it. What we will talk about, right, is how to interpret it, right? Like how do I know? What are some theories? Yeah, examples, analogies we can use to describe this. So you can imagine maybe we can say, oh, perhaps the acid's influence is too strong. Because it's a strong acid with base titration. Perhaps the acid's influence is too strong, even though the neutralization has occurred completely, right? The end result is that the solution is acidic, right? So maybe let me write here. Influence of strong acid is overwhelming. So as a result, the whole thing ends up being acidic. Okay, this is just an analogy. Don't treat it as gospel because in H2 Chem, you learn exactly why it's like that. But for us, right now, Sec 4, Sec 3, we are only going to learn about the shapes and the characteristics. For weak acid, strong base titration means I'm going to add a weak acid, but I start with a strong base, which means I'm still somewhere here. But when I end off, right, it should end off somewhere here because the weak acid, it's not going to go to 1 or 2, maybe 3, 4, 5, 6, the pH. Where's my endpoint? Here. Endpoint pH is greater than 7 actually. Again, a strange one, right? So why? Again, an analogy for you could be that perhaps the strong base influence is too strong. Influence is overwhelming, such that the entire mixture, the entire solution ends up alkaline instead. So the word overwhelming could be in inverted commas. Okay, so end up greater than 7. So in fact, you only need to learn about these 3. The 4th one is actually basically quite worthless because the graph looks a bit like this. You really can't get anything out of it. You can't find endpoint. You cannot find pH. You cannot find the amount of acid add to neutralize. You cannot find anything. So there is nothing here, which is good because you don't have to worry. You do exams, right? You need to focus on the other 3, right? So these kind of questions will never come up, just for comparison's sake only. Yep. Okay, and as for indicators, right, you know that you shouldn't use universal indicator for titration because what we want are sharp changes in colors at a certain range, right? So if I put universal indicator inside the titration, I wouldn't know where to stop, right? I drop, like the color changed slowly, red to orange to yellow to green to whatever. How I know where to stop, right? How green is green? Your green and my green is not the same, might not even be the same, right? So I need an indicator, a substance to add in, right? To really have this single snap change when that one drop is added. Okay, so this is why. Yeah. In this page, we can see, right, the common indicators that we use and what is the working range. Means if the pH falls within a certain range, right, that is a pretty good indicator to use really. So let's fill in the blanks first. The ones that we learned, the very common ones are methyl orange, which is red in acid, yellow in basic. Phenolphthalein is colorless in acidic and pink in basic. So for your syllabus, right, perhaps these 2 are more important because nowadays they don't really use phenolphthalein in titrations. So just take note of that. So what does that working range thing mean? It means that if I have a graph that looks like this, the sharp drop occurs somewhere around here. I would say between 6 plus to, I guess, 11. If my indicator can fall within this range, means it can fall within this 6 plus to 11, let's say 6 to 11. I can use it as an indicator. Okay, and that's the idea, right? So let's go to the previous page and look at another example. Can you see there's certain things here that we use, right? Methyl orange is good for a very generic kind of titration, simply because for this guy, his endpoint is definitely less than 7. Yes, this range, I would say maybe between 2 to 8, maybe 2 to 9, maybe, I don't know, 2 to 8. So if that is true, methyl orange is good. I can't use phenolphthalein because phenolphthalein too high, right? Similarly, for this particular titration, I can't use methyl orange. Methyl orange works around 3 to 4, right? It will fall outside of that sharp drop. I want it to fall within the sharp drop to tell me where to end the titration. Where has it stopped? Yep. And as I mentioned just now, useless weak base, weak acid titration looks weird, right? Because you can't get any information out of it. There's no indicator. There's nothing you can do. Okay. Now let's end off today's session, right, with some questions. Okay, and we'll call it a day. It's been quite a long day for you. Right. Let's do it. Question 1. Okay, get ready. Which statements are correct? Okay, for methyl orange indicator. One turns red, one turns yellow. Methyl orange is here. Right. So let's go through one by one. Solution U has a higher pH than solution V. Okay, is that correct? Let's see. So methyl orange is red in acidic, yellow in basic. So if V turn yellow, right, it means that this is sort of the basic color, the other color really, which is pH is higher than 4.4. If it's red, right, it's probably lower than 3.1. So does solution U have a lower pH than solution V? Yes, true. If 1 is true, then 2 is false, because it can't be both higher and lower. So this is gone case. What about 3? If U has a lower pH, it means it is more H+. Remember what we said just now? H+ is a measure, pH is a measure of how much H+. The more H+ there is, the lower the pH. So clearly this is wrong. Because if U has low pH, it must mean that it has a higher concentration of H+, 1 and 4. The answer is B. That's it. Question 2. Excess nitric acid added to sodium hydroxide. Acid-alkali reaction. Means I started with NaOH. Just add 2. If I started with NaOH, right, this is gone already. Right? Because it means starting pH must be high, 14 maybe, because NaOH is a strong base, strong alkali. But if I excess, it means that it's just like a normal titration kind of curve. As I add acid, there'll be one drop that I add, right? One little bit that I add that causes the entire thing to neutralize. And if I spam even more excess nitric acid, it will cause this thing to go all the way to acidic. The answer is D. Question 3. The indicator can distinguish. So look at this indicator. It's red, green, dark blue. What is it good for indicating? Let's look at A. Not good. Because this guy is a weak base. His pH or ammonia is around 9, 10. NaOH is around 13, 14. You cannot make it because it's already dark blue from 8 to 14. That's not good, not a good answer. What about sodium chloride and water? Okay, this is even worse because both are neutral. One is water, one is salt water. One is salt. So no, can't even tell them apart. What about C? Sodium nitrate and sodium hydroxide. This could be possible because this guy is strong base, strong alkali, sorry. So I will say 13 to 14, which means it will be dark blue. This guy is neutral because it's just a salt solution, which is about 7, which is green. I can't tell apart. The answer is probably C. Let's double check using the last one. Dilute acid. Both of them are strong acids. They are both red. I can't tell them apart because they are both strong acids. So confirm that the answer is C. Question 4. Okay, added to Z. Z is here, starting, right? Added to Z. If Z's pH starting is 1, Z must be acidic. So I'm going to take this out first. It's going to rise to 14. The more Y is being added, which means, right, between B and C, right, B is the better answer. Why? This is very interesting. Why is B the better answer? Why is it not D? Because imagine if I added insoluble metal oxide. Let's say, for example, it's let's say Z in this case is HCl. Let's say I add insoluble metal oxide. What insoluble metal oxide do I have? Copper oxide, for instance. If at this point, right, I added enough to neutralize it completely, what do I get? I get this and water. What I'm trying to prove here, right, is that at this point, right, there is no more acid left because all of it will be neutralized already, right? All right, here, no more acid. All neutralized already. If I were to spam this some more into a beaker or conical flask containing only salt and water and no acid, that CuO, that insoluble CuO, cannot dissolve anymore. So why would that cause the pH to increase, right? You flip it around, and what if I use a soluble metal oxide, such as Na2O? So the same logic happens. At the start, the reaction produces salt and water, sure. At that midpoint, the pH 7, all the acid is gone, yes. But if I continue to add the soluble metal oxide, the soluble metal oxide can dissolve in water to form an alkali. Alkali contributes OH to the solution, which forces the pH to go higher. And that's why the answer is B. Okay. Next question. State what is meant by a weak acid. Okay, just ask you to really go and remember what's the definition of weak acid. So a weak acid, partially, incompletely, dissociates in water to produce, water to produce a small amount or concentration of H plus ions. This is the exact definition for weak acid. We write a chemical equation to show the reaction between phosphoric acid, this is phosphoric acid, and calcium carbonate, acid carbonate reaction. What do we get here? We get calcium phosphate. This is like that. So we do a crisscross. And water and carbon dioxide. So I'm going to balance it a bit. Okay, so this is my answer. Okay, suggest why acids, right, such as sulfuric acid and nitric acid, are not used as descalars. So this one uses a weak acid, ethanoic acid, weak acids. We have phosphoric acid. What is the descaler? Remove some carbonate from the inner surface of the kettles. You know, when you go to a hotel, right, you can see a kettle, you go look inside. Sometimes there's some white coating, white solid inside, probably because due to the buildup of minerals over time, right, you have some carbonates that are stuck on the surface. So in order to get those things out, we will rinse them with some very, very weak acid like vinegar or something, just hope so that they'll react. I can't use a strong acid because what if the strong acid end up reacting with the kettle itself, right? Then I'll ruin my kettle, right? So let's use the answer. These are strong acids. The sulfuric acid and nitric acid are strong acids, which will cause a reaction with the metal in the kettle after the scale is removed. So that's that. Question 7. A solid wire dissolves both acids and alkalis without evolving any gas, right? So if I say solid W can react with both acids and alkalis, right, probably means that it's amphoteric. Let's put that in the back of our heads first. But it doesn't involve any gas. So what could it be? It cannot be this. Because copper things are not amphoteric. But zinc, yes. So is it zinc oxide or zinc carbonate? It is not zinc carbonate. Because zinc carbonate reacts with acids to form CO2 gas, which is not what we want, because we want something that does not evolve a gas. So the answer is D. Because zinc oxide literally just reacts with acid to get salt and water. Nothing there. Okay. last question, I think. Is that my last question? Yes, that's my last question. Okay. So a long chunk of words, right? Okay, these kind of questions are becoming more and more common in WAs and exams nowadays. They like to give you a long chunk, ask you, okay, this student is doing this experiment. Something wrong with his conclusions or with his procedure, and you tell me what is wrong. So that's what's happening. Okay, so let's read. Student compared the electrical conductivity of 3 acid solutions of the same concentration. He was asked to explain why sulfuric acid is better than HCl, which is in turn better than ethanoic acid. And he wrote this thing. Hydrochloric acid and sulfuric acid are weak acids. Ethanoic acid is strong. They conduct electricity as they produce hydride ions in solution. The mobile ions allow the acid solutions to, the mobile ions allow the acid solutions to conduct electricity. As sulfuric acid produces thrice the concentration of hydride ions, then hydrochloric acid, it is better as a conductivity. Several conceptual errors. Identify 3 and explain why they are wrong. So clearly, right, as if you have been following, right, if you know your stuff, as I go along, right, the words I highlight, clearly some of them are misconceptions. Let's identify them. This one is one of them. Clearly, you know that it's the other way around, right? Hydrochloric acid and sulfuric acid are both strong acids. It's ethanoic acid that is weak. So let's say that HCl and H2SO4 are both strong acids, while ethanoic acid is weak. If you can't write out a formula, it's fine, just write the name, it's okay. Ethanoic acid is weak. Error 2, this is the one. Very egregious, right? What hydride ions? Hydride is like that, H minus. It doesn't produce H minus, it produces H plus, right? So they produce, all the acids in this case, produce hydrogen ions, which are H plus in water, not H minus hydride ions. Okay, last one. This one is the weird one. Thrice? Really? If you know that sulfuric acid is H2SO4, right? Then of course you know it's not thrice lah. Sulfuric acid does not produce thrice the amount of H plus ions. It is, of course, dibasic. So it produces, so actually it's supposed to produce only twice the amount of H plus compared to HCl. And so that's that. Okay, so the next section here, right, is actually salts. But if your school hasn't done salts, right, it's okay. We will stop the lesson here. And if salts are a thing, right, okay, please consult your teacher. Perhaps you can arrange a consultation with your teacher, with your tutor, to go through salts briefly, because I think most schools will do acids and bases and a little bit of salts, but not so much about the salt preparation. Okay, so just a quick recap today. What have we learned? Where are we? All the way up there, so many pages. Okay, we have learned a few things. We learned acids and bases, alkalis as well. So what are some terminology? What's the difference between a strong acid, a weak acid, strong base, weak base? What is monobasic? What is dibasic? What are some reactions, common reactions of acids, common reactions of bases? Okay, what are they? What are some properties that they could have? We learned a little bit about the pH scale, learned a bit about the oxides, why we cannot add fertilizers and bases at the same time. How do I classify oxides into the 4 subcategories? What does it mean to be an amphoteric oxide? We learn about titration. How do you do titration? What are some things to follow? What are some graphs to look at? What are some important points that one take note of when maybe sketching a titration curve? What's the difference between these 3 or 4 titration curves? What is the indicator I should use? What are my considerations? What are my criteria? And that's it. Okay, hopefully this was useful for you. And I think that should be fine. Okay, all the best for your exams, okay? Yep. Bye-bye.